is 3.3. So we're going to look at derivatives and how they affect the shape of a graph. So we graphed in pre-cal. We found our x-intercepts. So we're going to do that same thing. And when we found our x-intercepts in pre-cal, we had a line. So here's our graph, and we found the x-intercepts. I think I talked about this in the video or the video before. And then we tested numbers in between and on the outside to see what our graph was doing. And I just told you, okay, if you plug in a number here and you get positive, then it's just coming down through this point. And if it's negative here, that means you're eventually going to go negative. So I don't care how low you go. You can go that low, or you can go even lower, right? I said I don't care. You're going to find out in calculus. So now in calculus, we're going to find out how low we're going to go, because we know when it makes a curve right here, at this point right here, we know the slope of the tangent line is 0, so we can set our derivative of our function equal to 0 and find out what this x value is. And once we know that x value, we can plug that into the original to find out what the y value is. And we can graph that point. So now we're able in pre-cal to graph the x-intercepts. And now in calculus, we know how low or how high we need to go on our little dips here, or if we have a hill or valley, we know how high and low to go. So we're going to put it all together, graphing, and how that derivative affects the graph. So there's quite a few rules as well as we go through this. It's called, or rules, they're called test. So we have like increasing and decreasing test, and first derivative test, and second derivative test. They kind of tell us what's happening in our graph. So increasing, here's the math lingo for increasing and decreasing. So if a function is increasing, that means its derivative is greater than 0, right? Because if it's going up, here the slope is positive, right? Because I'm going up, so it's increasing. So that means my derivative would be greater than 0. And if it's going down, that means my slope is negative, and so that means that I am decreasing. So you can take the derivative, set it equal to 0, which you're going to have to do to find these points anyways, and then just test it on a number line once you have those critical values. Test it on a number line, test to the left and test to the right. If this is negative, that means you're decreasing till this point, and if it's positive, that means you're increasing after that point. Okay, so basically that's what you're going to do with the increasing and decreasing test. That will come up. Okay, so then there's this first derivative test, and again, these are things that you've already done. They're just kind of a list of things that you need to step through one at a time. So they're kind of like steps, basically. So again, but it's all about taking the derivative. So we're going to take the derivative, f prime, right? And so basically what this says is, and you kind of, there's a couple of these tests that you don't really have to do. I believe it's the second derivative test you really don't have to do, because you can find out other information. But what this basically says is, if we go from if we find our critical value and we go from positive to negative, that means that we're going to have a max. Let's see. If we go from positive to negative, so that means I'm increasing and then decreasing. That means I'm going to have a max, which makes sense, right? Because you're going up and then coming down, so that means this is going to be max. So this is kind of self-explanatory. Or if you go from negative to positive, that means I'm decreasing and then increasing, so that means I'm going to have a minimum. This last part, third thing, if it doesn't change, that means you have something like this to the right, and it's called monotonic, where it's increasing, and then after that critical value, it's still increasing. So if that happens, there is no min or there's no max at C. It's called monotonic. So the first thing you're going to do, here's an example, is you're going to take the derivative, just like we have been doing. And just like in 3.1, we're going to set that derivative equal to 0. So let's go ahead and take this derivative, set it equal to 0, and then solve. A lot of these times, the only terrible thing is when you have a cubic, okay, and you have no x to factor out. That's the hard part, and that's when you got to find your factors of your constant divided by your factors lead coefficient. Use synthetic division. So those are the hard ones that you have to do. But this one's not going to be that hard, because you're still going to have an x here. When you take the derivative of 5, it's 0. So we're good there. We have an x in all of them. So we set that derivative equal to 0. Here we can factor out an x. So there's one of our critical numbers, 0. And now I can go ahead, I could probably factor out of 12 too, right? Might as well. Factor out of 12. And then minus x squared, and that should be x cubed. You're probably telling yourself. And it's minus 2. No more x. Okay. Okay, so that's set equal to 0, so that means 12x is 0. And x cubed minus x squared. So you were probably right the whole entire time, and I was wrong. Because you're never wrong. Only I'm wrong. No, I'm always right. Okay, anyways, so what factors of 2 that subtract 1? That'd be negative 2 and positive 1. So set those equals 0, so that means x equals 2, x equals 0 from that one, and x equals negative 1. Okay, so there's our critical numbers. So we might have maxes, we might have mins. So we're pretty much using what we did from 3.2 and 3.1 in 3.3 here. So we solve for x, we're going to put those on an interval. So we put those on a number line. So we have negative 1, 0, and 2. Should be a little space. Probably that should be 2. That should be 1. If I'm spacing correctly. Okay, so pick numbers to test and write down your intervals and find your max and min. Again, we could just put these numbers into our equation and see which one's the largest. And it could be a relative min or relative max or an absolute max. We don't know because this function continues. And we know it's a cubic, so we knew it looks something probably like this. Right, so it's probably not going to have any absolute maxes or absolute mins. It's probably going to have a relative, but we need to check to see maybe this is monotonic here at 0 or at 2. Okay, so we need to test. We can plug in negative numbers, big negative numbers, and see what happens. This is to the 4th, so it actually doesn't look like that. Somehow it's going to come back around. Right, so I can look at that and say that's how it's going to look, right? So I know from here it's going to go up, and I know over here it's going to go up because I have a positive x to the 4th. So I know it's going to look something like that. But I want to test numbers in between here. So I'm going to test, say, negative a half, which is not fun to test, especially if you're plugging it back in here. So you can do 2 different ways. One way is to use synthetic division. So I'm going to take 3. Oh, sorry. I'm actually not going to put it in the original one to test it. I'm actually going to test it in the derivative. So since I'm testing the derivative, I can just write my factors. X times x minus 2 and x plus 1 equals 0, right? So I can test it in here, and it doesn't equal 0. So we're going to see what this is. So I use my factors that I came up with rather than plug it in there. So that's one way to do it. Another way is to take the coefficients. So we had 12, negative 24. So 12, negative 12, negative 24, and then 0 for our constant. So again, this is the derivative. So this is f prime. So I'm going to see, I'm using the first derivative test. So either one of these would probably be the easier way to plug it in. All right, and I'm testing 1/2. So either one of these is fine. This one I like more just because I'm dealing with positive and negatives. I don't really care what that value is. So, because I'm just finding the slope. So I like this one because this, when I plug it in here, I get positive. Here I get a negative. And then here I get a positive. Or sorry, it's a negative actually. This is a negative. So I have a negative here because it's a negative 1/2 is what I'm testing. And a negative here, it's still positive though. So a negative times positive is a positive. So that means my slope is positive, okay? So my slope is positive. So it's going to be positive slope, okay? And then I test another number. So how about we test 1? Let's test 1. So this is still negative, this is positive, and this is positive. So that is a negative in between here. So in between these critical values, we're going from positive to negative. So that means our graph is increasing and then decreasing. So that means we are going to have a relative max at 0. Okay. Now, over here, I still need to test actually over here. So I need to test over here at -2 because I'm using that first derivative test. So at -2, plug in -2. That's a negative. That's a negative. And that's a negative. So negative times a negative times a negative is a negative. So that's negative. And then we're going to test at 3, say at 3. That's positive, 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 so it's positive. So what happens, we go from negative to positive. So if we ever go from negative to positive, that's a relative min. So I have a relative min at -1. And I go from negative to positive out here on the opposite sides of 2. So at 2, we're going to have a relative min. And then I go from positive to negative, so that is a relative max. So we have a local min at -1 and 2, and a local max at 0. So this one, we don't even have to graph. So all we have to do is just put those critical numbers on a number line, test numbers into the derivative, to the left and to the right. So this part probably right in f prime. So pick values to test in f prime. So we're picking values, testing them in f prime. Okay. Okay, so another test that we do is a test for concavity. It's basically kind of the shape that we have. Is it facing up or is it facing down, kind of like a parabola? Okay, so concave up means we have a valley. The U is facing up. Concave down, it's facing down. So we have a hill. So here, this would be a local min, local max. So here's the definition for it. And so a test for concavity is pretty much like the second derivative test. So you can use one of these tests. You don't have to use both of them. So you can either test for concavity or you can use the second derivative test. It's really the same thing. Okay, so if we take the second derivative and set it equal to 0, and then if it's bigger, that means we're concave up on our interval. I just stands for interval. And if it's negative, that means it's concave down, so it faces down. So we can go ahead and do an example of this. Or here's the second derivative test. So the second derivative test, again, it's taking the second derivative and the first derivative, so it's kind of a lot. So you got to take the first derivative and the second derivative. And what we do is, once you find the first derivative and you set it equal to 0 and you find your c, you take that c value and you plug it into your second derivative. And if it's bigger than 0, that means you have a local min at c. So instead of testing on a number line, so I guess you can use the first derivative test and put it on a number line, or you can just use the second derivative test. So instead of taking your critical values and testing to the right and to the left and seeing if it goes negative positive or positive negative, or if it goes positive positive or negative negative, you can go ahead and just take the second derivative and plug your c that you found, that critical value, into your second derivative and see if it's bigger than 0. And then if it is, then you'll have a local min at c. Or if it's smaller, then you'll have a local max. So instead of the first derivative, you can jump down to the second derivative. And then inflection points. So if the graph changes from concave up to concave down, or concave down to concave up, then there's an inflection point at that spot. So what this usually looks like is something like this. So at this spot right here, we have an inflection point. So these are all the values that you have to find when you're graphing. You have to find your x-intercepts. You have to find your maxes and mins. You have to know where it's concave up and concave down. And then you have to find these inflection points. So a lot more than pre-cal. All right, so here's an example. So we're going to go ahead and do the concavity test here. So we take the first derivative, and then we're going to go ahead and take the second derivative. And then here we can go ahead and factor, right, because there's an x in both of them. So we factor out an x, or factor out a 12x. a little bit easier. Set it equal to 0. And then we're going to put those, set that equal to 0, so x equals 0. So that's one of our numbers that we're going to test on each side, and then x equals 2. So we're going to test, say -1, in between here is 1 and 3, so we're going to test those three numbers. So I plug in a -1 here, that's a negative, plug in a -1 here, that's still negative, so we're positive, so that means we're concave up. So that means our graph faces up from to the left of 0. I'm facing up until I get my x value of 0. So let's go ahead and just put that on the same graph. So I'm facing up, and now I plug in 1. Well, I plug in 1, that's still a negative, but that's a positive. So then so that's negative. Positive times negative is a negative. So that means I'm concave down. So here was up, here was down. So now I'm down between 0 and 2. And then at 3, plug in 3, that's a positive, so I'm positive. So I'm back to up. So I'm back to facing up. So that's what maybe my graph looks like. But at these two x values, at 0 and at 2, I have inflection points because I went from up to down and down from up. So these would be inflection points. And there's our concavity. So concave up, our parabola shapes up, down, faces down, up, back to up. So in summary, basically there's a few derivative, you can call them derivative tests. We have the first derivative test, second derivative test. First derivative and second derivative are kind of similar, except for the second derivative. Of course, you have to take the second derivative. And but that can tell you whether you have a max or min, where the first derivative you have to put on a number line and test to the left of the critical number and to the right to see if you have a relative max or relative min. Or the second derivative test, you can find the first derivative's critical number and then take the second derivative and plug this number into the second derivative, and that will tell you max or min, so you don't have to do the test. And then concavity up is the second derivative, set equal to 0. Find those numbers, put them on a number line to test for concave up and concave down. So usually what I do is I either do the first derivative test and the concavity test, or I'll do the concavity test and the second derivative test to find everything that I need, because I need to find concavity, I need to find inflection points, and I need to find those maxes and mins. Okay, so that's it.